Testing. Testing. I do not seem to have audio. Where is my audio? I have levels, but no audio. Settings. That's not helpful. Let's just check if we're getting audio on Twitch. Seems like probably not. If we're not getting on Restream. Correct. Can we hear other things?
So if we're swapping, where is Lilia starting?
Oh.
I'm starting Raptors no matter
We
what.
can't. Oh.
Yeah.
Wait a second. So maybe we do have audio. Why can't I hear anything? How about now? Ah, perfect. Okay, we do have sound. Great. How about now? Ah, perfect. Okay, we do have sound. Great. How about now? Let's close that so that I don't drive myself crazy. And we'll edit that out later. And let's get started. Oh man, I am really happy that I didn't have to debug that. That was not what I wanted to spend my stream doing. Okay, what did I want to spend my stream doing? We're going to take a look at Glyphos, which is the app that I have been building for a while now and that I'm starting to share with other people. And the goal of Glyphos is to be able to do math on the computer, on the desktop, in the same way that you can do writing on the computer in a word processor. I know there are calculators, I know there is Desmos, I know there are spreadsheets. These are all for doing arithmetic, calculations, models. They're great. I love Excel personally. I think it's a great piece of software. I think anybody who doesn't is kind of fooling themselves when the whole world runs on it. But it's doing calculations. It's not doing math, pure math, the kind of math that mathematicians do, physicists do, engineers do, economists do. Of course, we want to be able to do things like, hey, 2 plus 2 had better be equal to 4. Definitely want to be able to do that. We want to be able to do more complex things. But we also want to be able to do things like 1 plus 2 times x plus 5 divided by y, and have that simplify the 3 in place. Again, okay, easy enough. What about, let's say that, well, I'll do the example I was doing the other day. A plus b times c plus d. We'll hypothesize that. It's going to get thrown into these statements over here. These are basically the things we are embedding into math land. So you can see when I hover over it, it says that the symbol types it works out what all the symbol types are. So the asterisks are multiplication, the plus is plus, and then A, B, C, and D are real numbers, and we've just hypothesized it. But we have all these transformation rules, and in particular, we have distributivity. So let's go ahead and use distributivity to say a plus b times c plus a plus b times d. And we'll try to derive that, and indeed it's able to derive it, and now that's added to the statements as well. And we can keep playing this game, right? Didn't like that one. Why not? Times c plus b times d. Parentheses, probably. Oh, I know what it is. I took some transforms out of scope because I didn't want to be cheating, because I've actually derived FOIL as a theorem before, and so it would just let us skip right to the end of this, which I didn't want to do. Okay, and we can keep deriving things. Let's drive all the way out to here, and you'll notice we can actually look at the transformation lattice, and you can see, I don't know why that sometimes doesn't want to open. I should look into that. So what you can see is that we started with, oh no, we cheated. Yeah, we cheated. We got to use FOIL directly, and so it's kind of showing us something wrong. Let me remove this, and let me go take FOIL out of scope. There. Remove that and rederive this. Why? Oh, did I just do the wrong thing? Derive. There we go. Derived. And now lattice. Really? Why is this all the way out here? Did I... That's not, that shouldn't be by hypothesis. Okay. Cool. So we took we started with a plus b. We used the distributive rule, distributive law, which is x times y plus z goes to x times y and x plus x times z. That got us to this split out version. Kind of interesting that it was able to do both of those in one go. Oh yeah, it can do both of those in one go. That makes sense. Okay, that's nice. So it actually applied the law twice in one step, which is cool, and is going to kind of get at what we're doing today. And then in the last step, these things are a little bit finicky, but in the last step, we split it out all the way, and we have this kind of FOIL. I don't know if other countries use FOIL as the acronym, but in the US, you're taught first, outside, inside, last, when you learn to distribute things like this, which always seemed like, why do I need an acronym for that? But hey, it's stuck in my head, and so in this case, I think it's like first, inside, outside, last, so it's file, but same idea. And we have this nice derivation, we have a nice provenance, and if we didn't already have this as a theorem that I proved it before, but we could turn it into a theorem, which then means we can use it directly. So if I put this transformation back in scope, and I remove these, and start from the same point again, I can actually just go straight to the answer, which is it that one? AC, BC, AD, BD. So we should just be able to derive this directly. Yeah, derive directly, and the law now is just FOIL because I have that proven as a theorem. One thing that would be kind of nice, I'm noticing that when I proved this as a theorem, I did it with A, B's, C's, and D's, but all my other transformations that I've put in here are in terms of X and Y. And I don't have a great way to like relabel this, but in principle you should just be able to relabel things. So I'm going to put that down as an FR for myself. So cool. That's the basic idea. We should be able to do, much more complex transformations than this. Goal is to eventually have latex support so that LaTeX, I never know how to pronounce that, but whatever it is, we should be able to display all of these symbols in a nice mathematical looking format rather than this more kind of coding looking format. Other goals are things like we should be able to do matrices. I think in principle we already could do matrices because all of the whole type system and parser is super flexible, so that the type system is defined up here, and so like we have real numbers defined, but we can define whatever types we want. They fit into a hierarchy, and then we can have different interpretations, which basically tell the parser what the notation is. So if I type in a plus, that it'd better be infix, so it better be between two things. It's got a precedence, so we have order of operations built in here. So for instance, multiplication is higher precedence than addition. Similarly, subtraction is the same precedence as addition. So, PEMDAS, another acronym that they taught me in school that is marginally more useful, I guess. So then, and again, this is all user defined, so this is really straight, like quite flexible. And then all of these can be exported and imported, so we can have a context of real numbers, which is what this one might be, but we could also have group theory, and we could have linear algebra, and we could have quantum mechanics, define Dirac notation in quantum mechanics. These are all things that we can do in principle, and I would say right now where I'm at with development is we can do a lot of things in principle, but the ergonomics isn't there yet, so it's like, how long would it take me to prove FOIL on paper versus this? Probably about the same amount of time. Maybe this is a little faster because I can copy paste and I can use, Vim controls, and it's in a text editor. And obviously I never have to prove it again once I've proven it. But if I tried to do the quadratic formula, for instance, I think it would still be a little bit tedious to do right now based on how things are built out. And one reason that's true is because right now there are situations like this. So we have the answer here, but this isn't quite FOIL, right? And so it seems like it should be really easy to just say we want this instead. That's FOIL, just to make it sort of the canonical version of FOIL. We want first, outside, inside, last. Whoops, that's not right. Last. There we go. And so we should be able to just derive that, right? But error. We weren't able to derive it. There are no valid transformations. Why? Well, if we think about what this statement really is, with all the parentheses, whoops, gets this nice green highlighting when it's exactly one of the statements, which, I don't know, that's a UI thing that I thought was a good idea earlier, and maybe it is, maybe it isn't. It'd be nice if it highlighted this one too. But anyhow, so like line 6, which is almost foil, it's foil in some other order, is really this, which has a bunch of parentheses in it. And we know that there's an associative law and a commutative law, which should allow it to go directly to whatever the parentheses are on this. But we can't do it in one step, because the transformations don't know that. If we want to do it currently, let's see what we have to do. We have to switch this and this. So we're going to have to unpack a bunch of parentheses, and move parentheses around until we're allowed to switch their order. And then even when we get the right answer, so just as an example, right now, what are these? So like actually, how do you even, let's see, so we could get rid of this and put the parenthesis here, and that's associativity. Not even. Why doesn't that work? We do something like w plus x plus y plus z. So this is something like a plus b plus c, and so we should be able to turn that into a plus b plus c, which would amount to w plus x plus y plus z. Is that not what I did? This thing, oh, this shouldn't be a paren. So it should be that, and then that. Yeah, okay, so we can derive that because of associativity, and then we have to do the inside, so then we have to go and get rid of this paren and this paren, and this one. And then finally we could do a times c plus b times, no, a times d plus b times c plus b times d, because commutativity. B? No. Why not? Shouldn't it be literally this, but this gets swapped. Anyway, I'm probably messing up, oh, there we go. Yeah, okay. So now we've derived foil, proper foil first. No, we haven't even, because this is still inside, outside. So we've managed to improve the situation by moving around one set of terms. I'm not going to keep going through this exercise. You can see, you get the point. This is tedious. This is not ergonomic. This is not what you would do if you were writing it down. If you were working at a blackboard, you would just say, what do you mean? Like, obviously, this and this are equivalent. It's just clear. So, in turn, what does that mean about our, well, how do we want to deal with that? Because right now, the way the engine works is you apply one transformation per derivation, and that one transformation might get applied multiple times. I think we saw that in this step. No, some step of the proof. we saw that in where it applied distributivity twice. Maybe it's somewhere up here. Yeah, this step we can do. So from here to here is 2 applications of the same transformation, right? In each case, we're using distributivity. We're just applying the same one twice. That's fine. And they're kind of separable also, in the sense that, like, we're not applying it over and over again to the same like within one part of the expression. I'm actually not sure if I had something like this. Let's remove all these. And so if I started with this, will it work for me too? So what does this expand to? Can I'm wondering if I can skip the step in the middle here. And if it's not obvious, nothing in the this is just a VS Code extension right now. The front end is just a VS Code extension. The back end is a REST backend where all the work is being done. At some point, I would like to make this web-based, but for right now, VS Code like gets me a lot of the front end things I need, and in particular, it's got this real nice text editor right in the middle of it, where you can work, and nothing matters, nothing is getting piped into Glyphos until you turn it into a statement. So we can type, whatever we want here, and nothing that doesn't affect anything. So anyway, my question is, this expression obviously expands out to this. Can I do this in one step? Yeah, I can't. Okay, that's what I thought. Because in some sense, that even though this is just 2 applications of the same rule, and it's 2 applications of the same of a rule we have, right? Like, so I can do this one at a time. Oh wait, what have I done? Are parentheses gonna matter? Is this gonna have the same associativity issue? Okay, there we go. Okay, so hang on, maybe we let's hypothesize this and then derive this. Yeah, okay, cool. That's what I expect. So even though we're applying the same rule twice, we need to do the intermediate step right now, because it's not able to apply that rule to itself once it's already done the transformation. Whereas in this case, this situation is kind of separable. It can, apply the rule on this side and apply the rule on this side, and it's not going to kind of step on itself. Anyway, what I'm really getting at is that we would like to be able to treat these sorts of expressions as just a bunch of additions and not have to worry about where the parentheses are, because we know that associativity is a rule. Okay. There's one other example of a similar phenomenon. Suppose we have something like, I don't know, something like this. And we want to evaluate it. That's not right. So I'm going to put it in as a statement. Now, I do just have a evaluate, and it'll just turn it. It'll just calculate the whole statement if it can. But you can see it didn't get added to statements because it's just doing it in place. This is more as like a helper tool to do calculations. If we want to derive this, it doesn't work to just derive it. We have to do each step separately. So 2 plus 3 is 5, and this will work. And then 5 times 7 is 35. And this will work. And then 5 plus 17.5. And that'll work. And then 22.5. And that'll work. And so it's like, okay, I don't want to have to do that. Again, the ergonomics of this seem bad. So these are two examples of the same problem, which is there are situations where it's really obvious that you should get to apply multiple transformations in one go, and it's so obvious that it makes the ergonomics really bad if you don't do that. All right. So what to do? Let's switch over to the back end. This is the back end, and the basic structure is there is a cli defined by all this. So there's a whole bunch of different subcommands that are defined. Hypothesize and add transformation, get transformations, and so on. And in the back end or behind the scenes in the VS Code extension, when you do different actions, it's calling the command line interface and calling these different commands. These commands, in turn, do a variety of things, but they tend to operate on a workspace. Actually, they operate on a workspace store, which is workspace transaction store, which has different types of transactions, transaction items, like adding a type, adding an interpretation, adding a hypothesis, removing statements, and these transactions then make everything undoable. So I probably used the undo or redo functionality a couple times while I was working on it. But the point is that the workspace transaction store, because it understands all of the changes to itself in terms of these transactions, and these transactions can actually, the items combine to form a transaction, which is the thing that gets undone. So if you have a command that removes a bunch of statements at once, those can be undone in one transaction. So the workspace store knows how to do all these things. The commands put together transactions, they stick them on top of the workspace store, and then the workspace store knows how to compile a workspace, which is what actually gets shown to you, and is kind of the fundamental state that we're operating on. So a workspace has types. It has generated types, which we'll talk about, but these are essentially, so the main example of these is numbers. You don't want the number 2 to look like every other real number, because it's not. For instance, whatever, x plus x is not equal to 4. 2 plus 2 is equal to 4. Those are different things. So there's a subtype of real numbers, which is 2. There's also a subtype of real numbers, which is 3, and so on and so forth. And pi, and 17 over 24, and so on. And we don't want to have to create those types manually. Those are generated types as you do operations that return real, like specific real numbers. They automatically get interpreted and turned into new types. And you can see this in the front end. real. So 35 and 22.5 is in here because of what we just did a minute ago. It didn't exist before then. If I undo both the statement 22.5 and the type disappeared. Let's see here. Interpretations are these. They tell the parser how to interpret things, and the transformation lattice is what I showed. It stores all of the ways that the statements get mapped via transformations. And it stores all the statements and all the transformations. Okay, so goal for this time, and one thing I want to do, let's see here. I'm going to add something to the scene. That's the best way to do this. Let's add something to the scene. I would like to duplicate this window. Copy. Paste. And then this one is going to be Obsidian. And I'm going to make it much smaller. I don't actually want the whole window though. Can I do it without the whole window? Filters. Maybe I can't do it right now. Maybe I'll have to figure this out later. Capture audio, client area, capture method, window. Alright, I'll figure this out for next time. I just wanted to I was gonna put something up that was kind of keeping track of our tasks as we did this, but maybe I can do it within. Oh, hang on, I have an idea. I don't usually mess with my okay, so what happens if I do this? Haha! Okay, perfect. Let's do it here. So goal. Does that show up? Yeah, that shows up. Okay. Auto magically apply transforms. How do I make this window wrap? That almost works. Toggle wrap. Hey, nice. Okay. Go away, little window. Thank you. Okay. Automatically apply transformation. Certain transformations multiple times in order to improve ergonomics. For instance, A plus B plus C plus D is the same as A plus B plus C plus D if associativity is the transformation. Is the idea. And so my approach then, and I was thinking through this earlier, and I think it works. Is to flag transformations with transformation hints, which, e.g., valuation, associativity, commutativity, which prior to checking applicable transformations generates new transformations with applicable starting points. Okay, what do I mean by that? For example, associativity. I'm gonna learn how to spell this real soon, I promise. Associativity, cool. Recognize that, let's use our example from above, A plus B plus C, B plus C plus D. As a statement is also A plus B plus C plus D, A plus B plus C plus D, etc. And auto-magically add those to the starting statements. So I think I lied when I was describing the general case. It should generate new statements. I don't want to save that as anything. Okay. And so these are going to have to be hard-coded in the sense that the logic for generating statements from associativity is going to need to be written into the back end. Same for evaluating. Same for commutativity, which is a downside. Like we've got this whole flexible we've got this whole nice flexible approach. Looking at my terminal and feeling like it's in the way. Yeah, I don't know how to move that out of the way. I don't really know how to sorry, I got distracted in my head doing Windows. Okay, so downside, we need to hard code the algorithms for checking if a type hint or a transformation hint is applicable and for applying it. Like there's no way to just work that out in general. Best alternative. Like some kind of alpha beta search, which tries to find the path between current statements and destination. So that would be I know we're like 45 minutes into the stream and I haven't actually coded anything yet, but spend time on design and hopefully it saves us time down the road. Alright, so if we did the alternative, this by the way is how I like to structure my design process. Like, here's a solution that I think works, what are the downsides, what's the best possible alternative, because sometimes you write down the best possible alternative and then you just decide that it's better and you do that instead. So the alternative here would be basically the equivalent of like a chess engine, where think about how a chess engine works. It knows its goal, right? Checkmate, or at least get to a position that it evaluates as better. And then it works out a path to get there by taking different moves. The trouble, and this is how I originally thought this would work when I first started this project, the trouble with doing it that way, I think, is that typically, so like if we go back to the app, there are, 4 statements and a lot of different transformations here. I don't know, 30 transformations here. So that's kind of like having 4 pieces on the chessboard and 30 valid ways to move any of them. Strikes me as, and this is like not a particularly complex setup right now. My concern is just that that's like computationally intractable. Like when I was futzing around trying to evaluate, basically I did something like a squared plus b, a squared times x plus b times x plus c equals 0, and then like let's define the quadratic formula as this thing, blah blah blah, or 2a, and like plug this in for x, so say x equals this, and plug it in and evaluate the whole thing, and like stuff was getting slow already as I was trying to plug it in and do the algebraic manipulations. And at some level that's unavoidable, because what to do, you can always add more statements and more transformations and eventually things are going to get slow. Some of that is also, I'm sure there are more optimizations than what I've done so far. I've done some optimization, but not much. But even with optimizations, I'm having a little bit of a hard time imagining an alpha beta search or something equivalent that would be effective. I'm also thinking, going back to or idea. I'm thinking that there aren't that many situations where you want to do this, really. Like, we've come up with 2 or 3 that are really common. But it's not like when you're working with, I don't know, if you're in economics and you write down whatever that's called, lambda optimization. I don't feel like we're like taking a whole bunch of shortcuts. Maybe in physics, if you write down wave functions, are you taking a whole bunch of shortcuts? There's weird stuff, like physicists do weird stuff, no offense to physicists, like manipulating the dr with like the differentials within integrals. Like, it'll be some like some like integral with a dot product of a differential inside the integral, which I think is like shorthand for something as a mathematician I would recognize. And so maybe there's some case for that being a situation like that's analogous to this one, where, you know, everybody looks at a string of additions and doesn't, you know, sort of mentally ignores the fact that there are technically parentheses there. So my point is, the strongest case for not doing this approach is look all over the place as people are using this thing. They're going to have situations where they want to automatically apply some transformations. And even if this is open source software, which it's not yet, by the way, but I would like to make it open source eventually, you know, is some physicist really gonna go and write the necessary algorithm to turn his integral with, or her integral with, a dot product in the middle of it, a dot product of a differential into the right thing? I don't know. My instinct there is just prove a theorem about it. You don't even have to prove a theorem about it, just put a transformation in there that is allowed. Like, the tricky thing about this situation specifically is that we don't want to. We could prove that these two are the same and these two are the same, but there's like a combinatoric explosion of things we would have to prove. We do also have arbitrary predicates right now, where you can say things like I think I have some in here. So like anything, this one down here means anything. It's a universal any because I have it being applied to any type. This is just probably crappy notation that I defined, but any statement that you have about O, and you also know that O equals X, then you can say the same statement about S. So this is called Leibniz law. It's saying, you know, if I tell you something about X and X equals Y, then whatever I told you about X had better also be true of Y. Right? It's like the defining property of equals. Equals means two things are the same. All we're talking about is labels, and you can relabel it. But this transformation is a little bit fundamentally different than some of these other transformations in the sense that, like, this, anything I can say about O is arbitrary. I could say 2x plus 5 equals 12, and then if I know that x equals y, I can also say that 2y plus 5 equals 12. I don't think that with those semantics, certainly it's not obvious to me that with those semantics I could do anything about the associativity problem. Yeah, no, I don't see a way. Yeah, I think this is an okay strategy. If I'm wrong about that, the reason I'd be wrong is because alpha beta search is really feasible. And I just don't know it yet. And that's fair. I wonder what ChatGPT has to say about let's see here. Under what circumstances are is alpha beta search an appropriate algorithm to use? Alpha beta pruning, search algorithms, use blah blah blah, min max, 2-player games taking alternate turns. Alpha beta pruning is useful in situations where searching the entire game tree is computationally impractical. Most effective when the game tree has a highly branching factor, and the order of moves can significantly impact its efficiency. You need good heuristics to explore the most promising moves first. Yeah, see, this is part of my issue. It's like, I don't know. What would my heuristics be? I can look at something and say, oh, I'm going to apply associativity to that. In fact, I don't even need to think that because mentally it's just flat in my head. I don't even think about the parentheses. But I feel like coming up with a heuristic, like one thing about this is that the transformation laws can be in different terms. So like one heuristic you might start to use is, does my starting point of my transformation look anything like my does my statement look anything like the starting point of my transformation? But they can look very different because the symbols can be really different, right? X, Y, and Z look very different than 5 and 7 and so on. And if you try to abstract away from that and just look at like the symbol tree, then you kind of lose all of that information. We can do it based on types. So we could forget. This is interesting. So what if we forget about the symbol
and just think about the types and compute some sort of difference. Heuristic. Abstract the symbol node to a type node, which forgets labels, and then compute some sort of Levenstein-esque difference. Then something like 5 plus b plus c and a plus b plus c, or x plus y plus z would be similar and prioritized in the algorithm. Sure. But okay, I'm actually starting to come around to this being a good idea. Maybe we should start with alpha beta search and see if we can get it to work. Because, like, 5 plus b plus c divided by 2 minus 12 would be less similar, but still similar enough to get tested first. Because, like, here's an optimization we could do. We just take the current way that transformations are looked at, and we sort them by this heuristic first. And we see how much that improves our speed. Do we have to worry that computing these things is slow? Not really, because we could cache the computation if we wanted to. Okay. I like this. Okay, changing what we're doing. This is why we design stuff. This is why we design stuff. Okay. Let's... Ooh. There we go. Let's check out the branch and do similarity heuristic. I already have some benchmarks, so we should pretty much for free be able to see if this improves speed of things. And so, why did this go all the way back up to the top? Go to the bottom. Alright, let's yank that for now. Goal. Implement a heuristic difference calculation to prioritize which transformation statements and transformations are considered first. Why is it? Okay. Go away. There we go. Okay, so let's take a look at the way that this works currently. So at the moment, when there is a derive command which takes the statement to derive and tries to derive it based on the statements that are in scope and the transformations that are in scope. Skipping down a little bit, try transform into here. So we scope down the workspace to just the statement scope and the transformation scope. And then we say, hey, transformation lattice, try to transform. Transform into, or should it tell me what the, it's this one, right? Yeah, transformation lattice, try transform into, does some checks, and then does some instantiation where it says some of these transforms are arbitrary. They have arbitrary, like the one that I showed before. I'm sure on my code, right? Yeah, okay. And so we've got to instantiate those into specific transforms. So that happens first. And then afterwards, we say for each transform, we're going to grab some candidate statements. We'll look at what that does in a moment. And then we're going to iterate through the statements. And we're going to try to use this transformation to transform from whatever statement we're looking at to the desired statement. And so the question becomes, can we determine, this order is somewhat random right now. The instantiated transformations come in whatever order they come in at, and the same thing with the candidate statements. I don't actually remember what this is doing. Oh, right. This is just handling the case where the transformation takes 2 inputs instead of 1. Okay, so what should our similarity metric be specifically? So a statement, I use statement and symbol node interchangeably, but a symbol node is really what we're talking about, and it has a root which has some data like the notation that's used and I don't know, some other stuff, and then it has children. So a statement like x plus y times z actually looks like x, like times y z plus x. It's like a little tree, right, where plus has 2 children, x and then times has 2 children, y and z. And this can go on to arbitrary depths. And so there's like a little forgetful transformation, a little homomorphism from this to something like, oh, and the symbol node root knows what type it is also. So there's something that goes to like plus real times real. And the point is that this should have a similarity score that's completely equal to, a plus y times z, or a times b times c, where those are real numbers, or 2 plus 3 times 5. Do we want those to literally have the same similarity score? Yeah, we do, because that means that they're applicable. So we want desired properties. If two statements have the same structure and types, they should get the same score. It's worth noticing, or they should get the top score. If they differ only by subtypes, they should get a good score. If they differ only by children, for instance, x plus y versus x plus y, they should get a good score. Do we want this thing to be symmetric? I'm actually leaning towards no. By symmetric, I mean if I'm calculating the similarity score between x and y, should it matter if I calculate it by x and y or y and x? So like, you know, you could compare two vectors by taking their absolute value and subtracting them, and it'd be symmetric. Which is usually what you want. You want a metric. This is sort of an interesting case, though, because so like, let's take the case of x plus y. So let's say diff or delta. We'll call the similarity. I guess we can just call it similarity. X plus y and 5 plus 3. If 5 plus 3 is the input, if x plus y is the input to a transform, and 5 plus 3 is the statement, these should be the same, because 5 plus 3 is a complete subtype of x plus y. But if it's the other way around, then they're not subtypes. Right, like a transform that starts with 5 plus 3, like the transform 5 plus 3 goes to 8, should not be applicable to x plus y. And there's another question, which is when I apply this thing. So let's say we're here. I typically know I know the statement, and I know I know I have a set of statements that might transform. I have a set of transformations. I want to order those two things as well as I can. And I have a desired statement that I know. That's one statement. So I probably want to compare the output of the potential transform to the desired statement and the input of the potential transform to the starting statements. I probably don't care about those exactly the same way. I would rather that my desired statement looks like the output of a transform. There's another problem too. My transforms can be applied to parts of statements. Right, so like, we would like to handle some case that's like, I don't know, A times B plus E times D plus E times F squared. I want to make sure that we do, that we apply associativity inside here, even though this symbol node looks like, you know, roughly this. And like this is what we end up wanting to apply to. So maybe we want the max. Okay, so if we walk the tree, yeah, so it's really not going to be symmetric. So, so let's say we're looking at the desired output. We want to compare that to the output of a transform. We're trying to order the transforms based on their ability to create an output. And so we want to compare the output. We want to get the max similarity between the output of the transform, between any subtree of the output of the transform, and any subtree of the desired output is what we'd like to do. That starts to be a lot of things to check. Because now, combinatorically, we're looking at yeah, so combinatorically then, we're going to look at each of the outputs of the transformations. We're going to look at the one desired output, and we're going to chase through their whole subtrees and compare them and get a max. Feels a little bit slow. Might not be too bad though. Okay. Okay. Let's So let's start experimenting. Let's go to symbol node and let's skip all this. One of my bigger types, probably too big. Get type map. That doesn't help anything. Okay, so the thought would be something like get similarity, self, other. F32. And since it's not symmetric, it actually feels like kind of an odd place to have it. Let's put it in transformation. So there's another issue. So there are different kinds of transformations. Mostly there are these two, explicit and algorithmic. And we really only want algorithmic is like computing, for 3 plus 5. I guess that's fine though. So let's say we have something like, again, we have to jump down to the bottom of this. It can't possibly transform into, okay. And what we want to say is, like get input similarity score, and this would be the input, and then we'll so this will be, let's just say to do, and then a similar thing that's output similarity score, and this will be output. And it'll be like match self explicit transformation key, then self dot compute say self dot compute similarity score t dot get from, and this is going to be a symbol node input, probably the other way on the arguments. Self algorithm. So if it's an algorithm, what do we want? If it's an algorithm and we're checking on the input, then how do we do that? Algorithm transformation might produce type. Can I not? I can't. Okay, fine. I'll look. Might produce type. Satisfies condition. What does satisfies condition do? There. Oh, input type. Oh, it's a generated type. The thing is, these should be really fast. In general, because they just bail. They bail really quickly. So I guess also, by the way, what do we want our, we have to go in 15 minutes. Our similarity score should go from 0 to 1, I guess. Has Levenstein do that? Sorry, I've been showing the wrong screen for a while. Still showing the wrong screen. There we go. How does Levenstein difference work? Minimum number. The minimum number of single-digit characters. Okay. So 0 is best. Fine. I'm okay with that. Right, they're the same. Okay, it's a metric, so it's, yeah, they're the same when it's 0. That makes a lot of sense. So if the number of children is 2, and the symbol is the operator, it'll be 0. And otherwise we'll make it 99 or something. Seems sane. So if input get children equals 2 and input dot type, that works. Assuming get symbol is the operator. Get symbol. Dot map. S is t dot get operator. Then 0 else. Similarity score maximum. And this can be an int, I think. And then for self, both sides. This we never actually use. Implemented. At some point we need to destroy that. Okay. And then to compute the similarity score, oh, let's throw this constant in first. Transforming similarity score, say max similarity score, U32, and we'll just make it a big number. Max similarity score. Okay, and then to actually compute this, I don't know. We'll do that later. Okay, so this is what the input looks like. The output will look like t dot get to output, and this is going to be if t dot the get algorithm type equals output get type evaluate to type, then 0 else max similarity score. Let's get to it. And then compute similarity score, and this will go from an input to an output, and return a U32. Oh, it should return a U32. Okay, let's just make sure everything's still compiling. Okay. Our input and output, really what I want. I think what I want is subtype and supertype. So the point is that the input should be more specific and the output should be more general. Couldn't compile, why not? Evaluates to type. Output, oh, shouldn't be a self. Oops. Come on. Mismatch types. Get algorithm type. What is algorithm type? Oh, that's not what we care about. What do we care about? Input type, operator. Okay, two things. One, we're going to need to know the type hierarchy. This is fine. This needs hierarchy. Okay. And then this needs hierarchy. And this needs to be hierarchy is subtype of so we need the output to be a subtype of the generated type. So t dot get input type get parents, and then output dot get evaluates to type. This needs to be a reference, and this needs to be parent type, and then we'll say this dot iter dot any parent type. Right, so now it's whenever the output type is a subtype of at least one of the parent types of the algorithm, then we say they're the same. That looks right. What's wrong syntactically? This returns a bool. We're just gonna go map error or unwrap or false. I don't mind it failing silently. Okay. Gonna have to go in a few minutes. So then, how are we going to actually compute this similarity score? Becomes the question. So we're going to look let's make this specific node general node. So we're going to take the max of something. So we're going to recurse and take the min score. Score equals So here's my worry now. Don't I just have a binary decision here? If the specific node fits into the general node, then we say they're similar. Otherwise, we say they're different. It's just binary. But when we get into alpha beta search land, that's not going to be the case anymore. We're going to want to have a way to say we're getting more and less similar. So that's what we have to sort out. Getting more and less similar. Okay. I think I'm gonna wrap up here. I gotta go. So let's go ahead and say intermediate state. Figuring out how to compute similarity score. Heuristic. And I will be back. I'm going to be back on Friday, but I think I'm going to use that more for demos and doing math within Glyphos rather than dev. So I think Wednesday mornings like this will be the time that I code. But anyhow, I'm going to wrap up here for now. Thanks for watching, the one person who stopped by. Appreciate it. And if you see this and you're interested and you want to like or follow, I would appreciate it. All right. Hope everybody's having a good day. Take care.